So one of the incredibly exciting developments at the moment is Quantinuum is coming to Singapore to open Singapore's first quantum computer. In fact, I'm very lucky to have with me today Dr. Jenni Strabley and Mr. Irfan Khan, who are the Vice President and General Manager for Compute Products at Quantinuum, as well as 20 years of experience in R&D for Jenni, as well as the Head of User Experiences and Intelligence Products and Compute for Quantinuum, Mr. Irfan Khan. And they're here to really introduce to us the amazing developments Quantinuum is bringing to Singapore.
Just a show of hands, who's used a quantum computer before? Great, great. Who's taken quantum mechanics in school? Okay. Who wants to know about quantum computers? Who wants to understand what's going on? Okay, great. That's what I was waiting for. Okay, so as said, Irfan and I are representing Quantinuum. Quantinuum recently made an announcement that will be growing a significant amount here in Singapore. So I'd like you to get familiar with Quantinuum and what we're doing and our technologies, because hopefully you'll be interacting with us a lot. So Quantinuum is about a 4-year-old company. I think we're celebrating our 4-year anniversary, but it came from 2 other companies that were decades old. So it was a merger that happened 4 years ago between 2 companies. One was Honeywell Quantum Solutions. So maybe you've heard of Honeywell. It's a large industrial. They had a group inside of Honeywell that was developing quantum hardware. And then there was a merger with a group in the UK called Cambridge Quantum Computing that was developing the software. And so overnight, this company was formed, Quantinuum, that was what we call a full stack quantum computing company. That means it's everything from the hardware, the basic metal, where all the quantum computing is done, all the way up to the application level. So what type of applications would you want to run on a quantum computer? That was 4 years ago. Today, we're almost 700 people in size. A fair number are PhDs and masters, but you don't have to have a PhD or a master to work at Quantinuum, and that will be the case also in Singapore. A lot of patents, so that's one way in a company. We do write a lot of technical papers, but we also file patents to protect our intellectual property. And as I said, a lot of papers. So 240 scientific papers and growing. You can look those up in journals or on the archive. And then we have a lot of domain experts that are in the company. So those are people who understand chemistry and materials, artificial intelligence, banking. Those folks really work on the software application side. I'm more on the hardware side. So I'll be able to represent that a little bit better. So we are a global company. We have a headquarters in the United States. I'm actually in Colorado is where I sit, but growing presence, and you can see a new site in Singapore, which we're very excited in. We also have a site in Tokyo and a quantum computer in Tokyo. This is a picture of our stack. So if you're not familiar with this type of picture, it's basically the types of layers of a quantum computer. So at the bottom is the hardware. And so this is a very simple box at the bottom, but it's actually very, very complicated. So it's actually the chip. That's where all the quantum computing happens. But to make that chip work, you have a whole lot of physical material surrounding it. So for our case, we use trapped ions as our qubit, 2 internal states in the trapped ion. And to make it do all the quantum information processing, you need a whole host of classical compute, lasers, optics, electronics, different types of things like that. So you have a lot of infrastructure that goes around it. As you go up the stack, we have a platform called Nexus. Irfan's going to be talking about some of the stack when he gets up to talk. We have some new tools that we released. These are programming languages and other tools to help programmers develop on the quantum computer. And then at the top layer are the application layers. So quantum chemistry, quantum materials, those are one of the first and emerging applications for quantum computing. You can think of those tools up there are to help chemists actually use quantum computers and develop code that would go on to quantum computers. This is our roadmap. So we've got our first quantum computer was released in 2020. And we have a roadmap that goes out into the 2030s timeframe. I'll talk a little bit more about the system in 2025 that we just released. It was called Helios. But then we have a system basically every 2 years, Sol, Apollo, and then Lumos in the 2030s. So you can see there the number of physical qubits. We just heard about the power of qubit. Every time you add a qubit, it grows exponential in terms of power. But we started with 20 qubits, then 56 qubits. 98 qubits is what Helios is. Moving on up into thousands of qubits by the end of the decade, and millions of qubits in the early 2030s. Very important on this chart is also something called 2-qubit gate error. So 2-qubit gate is really the heart of entanglement, and entanglement is really at the heart of what makes a quantum computer so powerful. And you want that error rate to be as low as possible. If that error is too high, then you basically don't get your quantum computer to do the calculation. It basically loses the quantum information faster than you can do your calculation. And so the 2-qubit gate error, you want it to be as low as possible. You'll have to put error correction on top of that to get it even lower. To do most large-scale applications, you're talking about an error rate, maybe 10 to the minus 9, 10 to the minus 8. So you want your physical error rate to get as low as possible, and then you'll use error correction on top of that to get the error rate down even lower. So just a little bit more about our quantum computers. So I said we had our first quantum computer, H1. It had 20 qubits, so those qubits are each an ion. And we use, again, the internal energy levels within the ion. These are called fully connected qubits. So that means that you can take any qubit and you can directly entangle it with another qubit. So that's a very powerful technique for both flexibility in making circuits. It's also a very powerful technique when you go to choose your error correction scheme. And there's many other interesting properties of it. So like mid-circuit measurement, we just heard a little bit about the power of measurement in quantum computing, the ability to make a measurement in the middle of the circuit. That's necessary to do error correction. It's also necessary for some state preparation. H2 then we released a couple years later. This is 56 qubits. Generally speaking, people say if a system has more than 50 qubits, it's very hard for it to be simulated by a classical computer. So this is narrowly in the regime where we should see things that a quantum computer can do better than a classical computer. And that's the fact. I think we have 2 or 3, maybe 3 or 4 demonstrations of people who have done things on our H2 quantum computer that are very challenging to be done on a classical computer. But you can see the 2-qubit gate fidelity for both H1 and H2, 99.9%. So that means about 1 time in 1,000, there's a mistake that happens in our quantum computer. And with error correction, you'll get that number even lower and lower. And then we just released Helios a couple of weeks ago. That's 98 physical qubits. Again, fully connected. That means any 2 qubits can be entangled directly together. Gate fidelity now is improved, 99.92%. I know that doesn't look like very much, but when you're doing a lot of gates, which is what you'll do in these large circuits, every 10th or 100th of a percent matters. Still all the same features and even some new ones. So real-time compilation. So now our classical computers and our quantum computers are very closely engaged with each other. And you're basically making decisions about the circuit in real time, how you're going to execute it. And Irfan will talk about that. And our qubits are pretty good. This is what users say about it. The best qubits on the market. It actually works. There's some quantum computers that don't actually work today. Ours actually do. Pretty popular quantum computers platform to use. Just to say a little bit more about Helios, I've said how the fidelities that it works with. We did a couple demonstrations with it, and you can see those are the preprints that we have down there at the bottom. Please take a look at those. But we did an algorithm called random circuit sampling. It's a specific type of quantum algorithm that is designed to specifically work really well on a quantum computer, but be hard for a classical computer. And we did such a hard problem of this random circuit sampling that if we were to try to do it on a classical computer, a supercomputer, that supercomputer would have to be powered by all the energy that comes from all the visible lights in the universe, or all the visible stars in the universe. So we're starting to get to the point where we're far, far, far exceeding, in this particular example, this particular algorithm, we're far, far, far exceeding what can be done with a quantum computer can do something better than a classical computer. We've started to look at more physical models. So we started to look at high temperature superconductivity. So if you're familiar with superconductivity, models work pretty well at very, very low temperatures, but as soon as you add temperature, it's hard to model what happens with a high temperature superconductor. In fact, it's hard to make it as well. And so now with our quantum computer, we can look at trying to understand the physics of what's going on within a high temperature superconductor, such that what we modeled with our Helios system would take over 2,000 supercomputers to fully store the information of that quantum state that we simulated with Helios. And there's the preprint on that work. So I won't get into some of our other tools, just to say that when we released Helios, we also released a new programming language. It's called Guppy. So some of you might have started to learn some programming languages. I encourage you to do that. But Guppy is a new programming language. It's programmed in something close to C, or close to Python, excuse me. So it's very, very user-friendly, but it has a lot of the important tools. And of course, this is the announcement here of Singapore, that our quantum computer will be coming to Singapore. And so the question is no longer if quantum computer will transform industries, but who will lead that transformation. We believe Singapore has really chosen to lead, and we're excited to be here. And with that, I'll also leave up this slide for just a minute. These are some of the open positions that we have right now in Singapore, ranging from working on the hardware or working on the software. So I'll turn it over to Irfan.
Hi everyone, my name is Irfan Khan. I'm a senior application engineer in the CPG group. The focus today is to describe how to access our quantum computer, specifically Quantinuum Helios. So as Jenni described before, we have our hardware at the bottom, and this is powered by a next generation control system. So this enables a more advanced execution model, which supports real-time decision making. And then on top of that is our job management and submission platform, Nexus. So that's the interface to actually access our quantum computer. And then above that is our developer suite, which consists of Guppy, a quantum-first programming language. That's Pythonic. It's embedded within Python, but it's not Python. Seline, an emulation framework to support optimization of Guppy programs, debugging of quantum computers. And then on top of that is our application suite, which consists of a quantum origin, a QRNG application solution in Quanto, which is another application solution for chemistry and material science, and then other programs that we work on in collaboration with other industry partners. Introducing Helios from a technical lens. So here I have a diagram of the Helios trap. So what you can see is a separation of the storage region and the logic region. And the point that I want to make here is this architecture is similar to a classical computer. On classical computers, you've commonly separated the storage region from the logic region, and this separation is enabled by the first junction that's enabling random qubit access. What we also have is a powerful classical computer coupled to the trap, and this contains a runtime that's required for real-time decision making. And then we also satisfy the DiVincenzo criteria. So we have qubits as barium ions. We have dedicated zones for logic initialization measurement. Within those zones, we can perform high fidelity operations via laser pulses on short ion chains. We cool all our ions, and we have all-to-all connectivity, as Jenni described, through physical transport. And then this is something that's scalable thanks to microfabricated devices. We have 98 fully connected physical qubits with 4 nines, 1 qubit fidelity, and 3 nines, 2 qubit gate fidelity. With Helios, what you have is the ability to perform on-the-fly native operations, such as transport, gating, and ion allocation. And then there's additional things. So you can have programs with substantial arbitrary control flow and classical compute. I'll come on to what that means later. There's also a mechanism for automated qubit resource management. So qubits is a scarce resource on Helios. You only have 98, and the system is responsible for how those qubits are allocated. And then a common enemy for quantum error correction is leakage. So we have a robust leakage detection capability that exploits the hyperfine structure of the barium qubit. In terms of pathway, Guppy is the application programming language, so that's a source language with which you can write a program, and then you submit via Nexus, and you can access Helios, Seline, which is an emulation framework supporting Helios, as well as H2. What we also support is an industry standard called QIR, the Quantum Intermediate Representation, and this is effectively making Helios software agnostic. So there are off-the-shelf tools, Microsoft Q#, NVIDIA CUDA-Q, ORNL XACC that use the QIR pathway. The QIR pathway also enables backwards compatibility between Guppy and system model H2, which is our other quantum computer, a previous generation. With Guppy, so Guppy is this quantum-first programming language, and that compiles to a compact graph-based representation called Hugger. It stands for Hierarchical Unified Graph Representation. And then we have a compiler to optimize the quantum operations in this compact representation. And then we continue to rely on Nexus for job submission and management. So that's a cloud platform with a Python API. PyTicket, which is our legacy tool, still exists, and that's to support third-party conversions from off-the-shelf tools into Guppy. So a PyTicket circuit would be a function in Guppy. So on this slide, I'd like to describe the semantics of the Guppy programming language. So all methods need to be annotated in Guppy. So all users require use of a Guppy decorator. So that tells your Python interpreter that this particular method belongs to Guppy. And then you also need to define method signatures. So all input types and output types need to be defined. Similar to programming languages like C and Rust and Java, there's an entry point function. So in this particular example, we've called it main, but that name is user specifiable. And then we also have a built-in result function, and this is a mechanism to tag measurement outcomes in order to report back to the user, but it's also a tool for debugging. So with the result function, you can tag integers, floating point numbers, booleans, and arrays over those types as outputs, and then they can also be assigned a user-friendly name. So in this example, I have the bell function at the top, which requests 2 qubits, and then performs quantum operations to prepare a bell state, and then it returns those qubits. In the main method, we call the bell function, we get those qubits, and then we measure, and then we tag the output using the built-in result function. We have to do a local compilation to Hugger, so this is for type safety, and that will complete successfully. And once you have that Hugger representation, you can run it locally on your laptop with Seline, or you could submit via Nexus to either hardware targets or emulator targets. So here I have a slightly more complete specification on what Guppy can do. So it's enabling arbitrary control flow. So in this example, so this is a repeat until success, we're using a bounded for loop with 5 iterations. You can also do while loops. You can do conditional branching as well, if statements, elif statements, else statements. So we use an if statement in this example to break the for loop. We also support arbitrary classical compute. but this does not include third-party libraries. And this classical compute is executed in real time. So what we support is integer arithmetic, floating point arithmetic, logical expressions, binary operations. We also have a random number generator that can be used in real time. We support a native universal gate set, so that's documented on our website. We have static compiling and safety, so this is ensuring qubit safety when users write programs with Guppy. And then we also have this idea of dynamic qubit allocation, where users can request qubits in their program, but it's actually the system that allocates ions. So in this particular example, we have a for loop with 5 iterations, and then we have a conditional block to break the for loop. Describe what that program looks like on the right-hand side. And what I want to show here is the non-uniform cost accumulation per shot. So what you do when you access a quantum computer is you write a program and then you repeat it n times to generate a distribution of measurements. And historically, the cost per shot is the same. With Helios, this is no longer the case. It's now non-uniform. So your first shot could consume 6.6 HQCs if you run all of your for loops. And then your second shot could consume 3.2 HQCs if your for loop ends early. And what this means is when users submit programs, they also need to specify a maximum cost, and we have a tool to do this. And then dynamic qubit allocation, so I just want to show you this. So users request qubits in Guppy, and then it's actually the system that's responsible for this. So all the requests in the Guppy source are virtual qubits, and then when you run this on the system, the runtime is responsible for the actual ion allocation. So we have a resource called a syntax checker, and we can submit to that resource via Nexus. And basically, what that resource does is it runs the user program, and then it generates the cost. And the cost is determined based on this formula. So HQC stands for hardware quantum credits. And this resource provides guidance on what the max cost specification should be. So it returns an estimate for the user to use. And then when it comes to job submission, users need to specify a configuration that takes in the max cost estimate, the number of qubits. And once you've defined that, so that's in the top cell, you can actually submit to Nexus. So that's the entire workflow. So there's a blocking mechanism that stops result retrieval until the job completes. And then once that's completed, you can request results right at the end. And then very quickly, I just want to go over the different compilation steps. So locally, users compile to Hugger, and then they submit via Nexus to hardware. And then in the hardware, there's 2 additional compilation steps. The first compilation step is lowering to a machine-native representation. And then the second compilation step is actually performed during execution of your program. So all the control flow in your program is like a filter function on the quantum operations that you stream to the trap. So the runtime is like a router, so it routes those operations to the trap. And the operations from the user program are operations like ion transport, physical gating, so lasers, as well as allocation of the ions themselves. And then in terms of job lifecycle, so the user always interacts with Nexus, so they submit a job, and then Nexus submits to hardware. There's a feedback loop to query the status, and then once the job is complete, the user requests the result from Nexus. So Nexus is like an interface to hardware. Once you submit to hardware, in order to perform at the required threshold performance, we have a chunking mechanism. So this basically breaks our jobs into multiple chunks, and each chunk is like a partition over shots. So if you have a job with 30 shots, and you have 3 chunks, then each chunk has 10 shots. Chunks can be interleaved with, and the idea here is you perform the appropriate machine actions around calibrations and checks to make sure there isn't any degradation in performance. What this also means is the time to solution for your job doesn't actually equal the true machine execution across all chunks. So here I list some of the actions. So there's checks, post-checks, time calibrations, and time validations. And if any of these fail during chunking, then we rerun things, or an operator intervenes and tries to correct the system. So you can have 2 types of interventions. You can have automatic interventions where the system tries to self-correct, or you can have a human interaction where an operator pauses the system, pauses the job, and then intervenes to try and correct the system. Just to summarize, so with we have our performance improvements when it comes to time to solution of jobs and the quality of solution. So this is enabled thanks to improvements within the trap and also with the new stack. There's better resource utilization and user experience using the trap. And this is a machine that has features that no other machine has available. And then we also have applications, so 50 logical qubits for a magnetism demonstration, superconductivity that Jenni chatted about. We've done a cybersecurity application with JPMC, and then we have an existing GenQIA program to combine quantum algorithms with LLMs. We have a documentation site, so this QR code will take you to our documentation site, so that has systems in Nexus, as well as a language guide for Guppy. And then finally, I just want to mention that in 2026, we will have topics. There'll be more that will be posted, and these topics are on Guppy and the new stack, as well as tips and tricks using Nexus to access our systems. Thank you very much.